periodic table. This is not. Okay. So one of the first things we're going to need to recall in order to be successful in this chapter is writing electron configurations. So do you all remember doing this? Probably from 1210. Let's start with an example. We're going to start with nickel because chromium and copper are both exceptions to the normal rule for writing electron configurations. I believe this is chapter 6 in your textbook, unless it changed from the last time I taught this. So take a look at that if you are, if recalling how to write electron configurations is a bit challenging. So again, let's start with nickel. All right, so when we write an electron configuration, we're essentially trying to figure out which valence electrons are available for reactions. And so the core electrons we care less about. So if we're looking at one, we can use the one on the wall. If we're looking at our periodic table, we want to figure out the electron configuration for nickel. We could go through and say, okay, we have 1s electrons, 2s, 2p, 3s, etc., right? But all of that stuff, most of that stuff are core electrons. So anything before argon, we'll write like this. So that represents all of those core electrons through the electron configuration for argon. And then we write the valence electrons. And these are based on the position of nickel on the periodic table. So if we're looking at the row that nickel's in, row 4, we have, starting with potassium, we're going to fill the S shell first, and that is, since we're in row 4, 4s. And nickel is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the 10th element over. We put 2 electrons in our s orbital, which means because it's the 10th element over, there are 8 more electrons in that d orbital that we need to fill. Does anyone recall what the first, well, no, let me just do it. 3d8. So this is one of those guess within my head questions that's not very useful for you. So we fill out the 3d orbital next, and the number of electrons is based on the position, again, on the periodic table. That represents the number of electrons there, okay? If you're wondering, again, what the electron configuration is for argon, it's 1s2, 2s2, 2p6, 3s2, 3p6. And that's completely filled. Okay? And it's a lot to write, and so this is why we use the shorthand with the argon in brackets. So for every transition metal in row 4, you can write argon in brackets, and then fill the d orbitals and then the s orbitals. If you go down to row 5, say you want to write the ruthenium electron configuration, you look at the noble gas above that row, so the one ending row 4, that's krypton, so krypton would be in brackets. Now remember doing this type of thing? Okay. I think it'll come back if it hasn't. I mentioned that chromium and copper are exceptions. And the electron configurations for these, let me write it out and then we'll talk about why it's an exception. So for chromium, again, row 4, so we're going to use argon in brackets. Then it's 4s1 and 3d5 for its electron configuration. Does anyone remember why this exception exists? Yeah, it has to do with stability, exactly. So our d orbital has these 5 places for electrons, right? 5 orbitals within that, so within that shell. And so when you put electrons in, remember electrons are represented by arrows that look like this. Having 5 electrons here is more stable than having 4 electrons like this, and then the other electron in the s orbital, and so that's why there would be this difference, this exception. So there's some stability associated with half filling the d shell orbitals, d shell electrons. And then for copper, another exception, its electron configuration is argon in brackets, 4s1, and then 3d10. Okay. Look at where copper is on the periodic table. It's the 11th position over. Again, that completely filled D shell has greater stability than if we would have only 9 there, 9 electrons there, and 2 in the s orbital. So this is another stability issue. Okay. Try writing the electron configuration for technetium, Tc. Take a minute, write that one in your notes. So if we look at technetium, it's in row 5. The noble gas before that occurs before that is krypton. So we'll put that in brackets. Then we're going to fill the 5 s electrons. Right. And we're going to have 4d as well. How many in each? Well, technetium, if we look, is 7th position over. Gives us 7 electrons to fill. We'll put 2 in the s orbital and 5 in the d orbital. Make sense? Cool. Again, like I said, if you don't recall how to do some of this, or you're feeling rusty, go back to chapter 6. There's a few more examples in that chapter. Okay. So when we're going to be looking at these transition metals, and we're going to need to consider their oxidation states. Again, harkens back to our electrochem. But what we're really thinking about with our oxidation states of these metals is how they lose their outer electrons. And typically, these metals will lose the s electrons before they're going to lose d electrons. And so that gives us some parameters for writing the electron configurations for the oxidation states. So let's first rewrite here in this table the electron configuration for chromium. And so that was argon in brackets, 4s1, 3d5. Chromium has, one of the oxidation states that's possible is the chromium 3+. So what we can do is write the electron configuration for that. Okay. When we have a 3+ oxidation state, that means it has lost 3 electrons from its original configuration. So the chromium 3+ electron configuration will have 3 less electrons than chromium. Okay. And so we're going to lose the s electron first. and then that'll give us 1, and then we're going to need to lose 2 more. So we're going to have argon in brackets, 3d3. Okay. Make sense? There's another oxidation state of chromium that occurs frequently. Chromium 6+. You may have heard of hexavalent chromium. It's an environmental pollutant. This is hexavalent chromium. It's the 6+ oxidation state. And in that form, that ion, all of the valence electrons have gone. So you'll notice compared to this electron configuration where there are 6 electrons in the valence shell, if we lose 6, we're essentially left with this electron configuration, just argon in brackets. So typically what we see with oxidation states is that they correspond with the formation of some sort of stable electron configuration, number of electrons lost and things like that based on the outer valence electrons. So with nickel, we had Ar in brackets 4s2 3d8. Nickel 2+ is a very common cation of nickel. So again, if we're writing the electron configuration of this, we're going to lose those 4s electrons first, those s electrons. And so we're going to end up with an electron configuration of Ar in brackets 3d8. Make sense? Okay. With copper, one more time, we'll do one more example. Original, sort of, the copper electron configuration is argon in brackets 4s1 3d10. Copper 2+ is a very common ion of copper. We lose 2 electrons in this case, 1 from the s, 1 from the d, and we'll get argon in bracket 3d9. So again, make sure you're able to do these electron configurations. Yes?
Will we always lose the S first?
I think there, let's see. Let's say yes. There's probably exceptions, but I think for your purpose, you're going to lose from S first. Okay. Yes. In that column? No, I don't. Actually, yes. Yes, so molybdenum and silver, yeah, because it has to do with those electrons, the stable electron configurations. Okay. So when we're talking about our d electrons, and I had drawn something like this to represent the d subshell, and electrons like this, you could have 4, you can have 5. If you have 6, then you start pairing them. Y'all remember doing this? Well, these subshells and the arrangement of the electrons in these subshells gives rise to some really cool physical properties of these metal complexes. As we've seen, they can give rise to more than one oxidation state. And this table shows the different possible oxidation states for various metals. I'm going to draw the copper electron configuration one more time. So we have argon in brackets 4s1 3d10. And if we look at this table, the sort of yellow-orange circle is the most frequently seen oxidation state, when the green ones are less common. And if you take a look at the copper configuration, you can see that if we lose one electron first, we're losing this s electron, okay? And so you can imagine then that having a 3d10 completely filled subshell would be pretty stable. And we do see a +1 oxidation state that would correspond with that. And somewhat surprisingly, I would say that the 2+ is actually more frequently seen, where we have argon and 3D9, but it is still possible to see the +1. And then also the +3 is possible as well. So you don't need to memorize these, but it's kind of an interesting thing to sort of look at the trends and look at how the electron configurations are changing with each of those. And so we mentioned, these electron configurations are going to give rise to different physical properties, including magnetic properties. We'll talk a little bit about that. And then give rise to colored compounds, which is actually pretty fun to think about, to play around with in the lab. So, thinking about cobalt 2+, nickel, copper, and zinc 2+. These are in the same order as the solutions in the beaker. So cobalt is red, nickel is green, copper is blue, and zinc is colorless. And each of those are the 2+ oxidation state, but if we take a look at their electron configurations, they are going to be different, which gives rise to different properties, including their color. The color has to do with transitioning of these electrons between different orbitals. We'll talk a tiny bit about that, maybe next time, maybe Monday, but very briefly, unfortunately. That's actually pretty fun stuff. Okay. Any questions on anything? Yeah.
Why is C2+ more power if it's less stable?
Well, I don't know that it's less stable. It just, using the rules that we've taught you, it would seemingly be less stable because it has that 3D9 as opposed to the filled shell. There's going to be some entropy reasons as well and some other thermodynamic properties that we're not going to spend time on, so yeah. Okay. Anything else? All right. So we've seen transition metal complexes. We saw these come up with solubility chapter and a little bit when we were talking about Lewis acids and bases. I want to make sure we cover a few terms here. So the term complex basically means that you have a central metal atom. And that is bonded to molecules or ions. I taught at Ohio Northern for a few years before I came here. And we had a lecture hall that was small, but it held about 50 students. And for some reason, they built this lecture hall below the dance floor for the people who do dance, like the tap people were upstairs all the time during my class, just tippy-tapping all around. Every day I would have to listen to while I'm teaching. It was crazy. Anyway, this sound is reminding me of that and having some flashbacks. Okay, so complex, central metal bonded to either molecules or ions. Complex ions then, we saw these again with the solubility. Typically increase the solubility of a slightly soluble salt. And so basically we have a complex with a net charge. So these are, this table has a large number of complex ions shown here, different iron compounds, silver, cadmium, copper, etc. Coordination compounds then are similar to complexes, but we're going to use a different term here as well. So again, these have a central metal. But instead of being bonded to a molecular ion, necessarily, we're going to say it has ligands. And what's a ligand? A ligand is a molecule or a compound that donates electrons to form the coordination compound. Okay. I think we talked about coordinate covalent bonds when we were talking about Lewis acids and bases. With that type of compound, the two electrons that are shared in a bond come from one species, one of the things that's going to be reacting. This is that same sort of definition. So coordination compound has a metal, and the ligand donates those two electrons to make the compound. We have a number of different ligands, number that you should be familiar with. Here we have 4. Here's water, ammonia, we have chloride, and then we have our cyano compound, or excuse me, cyanoligand, which is essentially cyanide. Okay, but cyano is the term that you use when you're talking about it in the ligand form. So make sure you're familiar with those. Okay. The other thing you need to start recalling are molecular geometries. You may not necessarily need to be able to take a molecule formula and then write the geometry at this point, but for sure, make sure you're familiar with the terms, especially these 4 at the bottom of the table: square planar, tetrahedral, trigonal bipyramidal, and octahedral. So square planar is a molecule that is within a plane. Tetrahedral would have a 3-dimensional shape but still has 4 things bonded to it. The difference between tetrahedral, why something forms a tetrahedral and why something forms a square planar, are the number of lone pair electrons. So you'll notice here in this diagram we have a central metal, 4 things bonded to it, and then 2 lone pairs of electrons. And those lone pairs would be located in and out of the plane, and their repulsion interactions are going to make the rest of the molecule become planar. Tetrahedral doesn't have that, okay? And so it forms a 3-dimensional shape and with certain bond angles that are make it so that it's equal around the central metal atom. And then trigonal bipyramidal, we won't see this one too much in this chapter, has 5 things bonded to it, and then octahedral, this is a big one. We will see this come up a few times, okay? So if we go back to our geometry table, when I say 6 things, I mean atoms. Okay, I don't mean electrons. I'm not counting those, I guess. So I should be more clear. So 6 atoms bonded to a central metal atom. Our only option, AX6, is octahedral. If we have 4 atoms bonded to a central metal, we could have tetrahedral geometry or square planar. We would have to find out if there are a lone pair electrons on that central metal atom in order to figure out if we have a square planar geometry. Okay. Does that help? Make sense? All right. All right. So all of our coordination or complex knowledge, a lot of it is based off of the work of Alfred Werner and people who worked with him, and the people who were nameless who worked with him and didn't get any recognition, which I could say about every scientist, not just him. But he basically came up with a theory that allows us to understand how inorganic complexes are formed and how to figure out their formulas. Let's see. So he also did these things before Lewis. who worked on Lewis structures and Lewis acid base types of chemistry. He did this work before that, which is kind of interesting. So he did like more experimental thing before then the theory came up with Lewis. And so one of the things that Alfred Werner did was he studied cobalt complexes. One of them being the cobalt complex with 6 ammonia, CO, NH3, 6, that's in brackets, Cl3. Okay. So he took a compound like this, and some of the analogs, we're going to use that term for right now, that have similar formulas. He dissolved those in water, and then he added silver nitrate to the solution. Why do you think he did that? What's going to happen after if you add silver nitrate to a solution that contains chloride? Anyone recall? You're going to form silver chloride, which is going to precipitate because it's slightly soluble salts, low solubility. And so what he was able to do is dissolve these cobalt salts, add some silver nitrate, precipitate out silver chloride, and then quantify the amount of chloride that comes from quantify the amount of silver chloride, which then corresponds to the amount of chloride ion that was in solution, which then corresponds to a formula for the cobalt compound. Okay? So basically what he was able to do is determine something called the coordination sphere. We're going to look at coordination sphere. So the coordination sphere is essentially, look at this cobalt compound, the way I wrote this. Okay, there's cobalt with ammonia in brackets, and then there's chloride outside of the brackets. Okay. Long story short is, Werner figured out that the stuff that's inside the brackets, those things are bonded together. So the cobalt is bonded to each of the 6 ammonia. And these chlorides are not bonded in any significant way. They are sort of associated with that molecule, but they don't have a covalent bond. Okay? And so when you dissolve them, what you end up with is cobalt, NH3, 6, and 3 Cl minus. Okay? So the coordination sphere is the thing that stays together when you dissolve the molecule. And everything else outside of those brackets dissociates. Okay, so that's essentially what he came up with. And then we're going to take a look at the next slide and look at a few of the other things that go into this. Spheres. The central metal atom and the molecules that are bonded to it. Okay. Now, in writing a formula, when we go back to, all right. So again, Werner had these cobalt compounds. They had different colors. And what he knew of the formula was something like this. So cobalt, 3 chlorine times 6 ammonia, and that was an orange thing, okay? And then you change it to have 5 ammonia instead of 6, and it changes color, now it's purple. And if you go down to 4 ammonia, green, but then there were 2 compounds that had 4 ammonia, and one was green and one was violet, okay? And so through some experimentation, what he found was that the number of ions formed per one of these, there's 4 that was formed here, 3 here, and 2 for each of these. And so what does that mean? Again, make sure I'm not getting too far ahead here. With the cobalt chloride with 3 chlorine, just like I wrote on the previous slide, oops, excuse me. I'm going to do some shorthand here. What he found was that there were 4 ions formed when he dissolved this orange compound in water. And those ions correspond to 3 chloride and 1 complex ion. I just left out the formula in there, but it is this, okay? And then with the one with the 5 ammonia, here we have cobalt, ammonia, 5 of those, and a chloride, Cl2 outside the bracket. 2 Cl minus is formed, plus CO, NH3, Cl, oops, plus 2. And so that cobalt compound is going to have an octahedral compound. This is an octahedral compound. It's going to have 5 ammonia, and then one of these white ones would be green to represent another ammonia, and the other one would represent the chlorine. They are all bonded together. The other 2 chloride are not bonded to the central metal atom. Okay? So that's the coordination sphere. Then when we get down to the green and violet, I think I have it on the slide here. They're going to look something like this, these structures. Sorry, it's a little blurry. We're going to have what we refer to as cis and trans isomers. And so these are molecules that have the same formulas, but the position of the bonds are different. And so we imagine that, again, these white spheres represent the chlorine, the green represent ammonia. Here we have our trans form, so across the central metal atom. And here we have the cis form, so on the same side of the central metal atom. Okay? Those are 2 isomers, so isomers have the same formula. In this case, different arrangement of atoms. All right? And interestingly, for these cobalt complexes, that ends up meaning they have different colors, okay? Green and violet, which is really cool. Okay, questions on that? Okay, so another term I want to point out is that of the coordination number. So again, the coordination sphere is what is bonded to the central metal atom, the things that show up inside the brackets. So then the coordination number is the number of atoms that are bonded to the central metal atom. Really the number of bonds to the central metal atom. So again, if we're looking at our trans form of the ammonia complex, where these green spheres represent ammonia, yes, each of those ammonia has 4 atoms, but the coordination number would be 6 because there's a carbon nitrogen, carbon chlorine, carbon nitrogen, cobalt. Sorry, black is always carbon in models, and that threw me off. But yeah, so the coordination number is the number of atoms bonded to the central metal atom. Okay. Other terms that arise from Werner's theory are that of primary valence and secondary valence. So the primary valence refers to the oxidation state, and the secondary valence refers to the coordination number. Okay, so these two things, coordination number and oxidation state, are going to allow us to sort of understand some of the properties of these metal complexes. Okay. So here we have pictures of a solution of two iron complexes. One is yellow. So this is the hexa-aqua iron complex. This is why we aren't doing naming, but get ready. So that's hexa-aqua iron. Okay. That one's relatively straightforward. And it's yellow. When we add a cyanado ion to thiocyanate ion to the solution, what we end up forming is a red solution. And this compound or complex is formed. And the name for this is penta-aqua isothiocyanado iron. So again, just be thankful we're not doing naming. But you can see we end up replacing one of the water molecules that's bonded to the central iron with this thiocyanate ion. Okay? And it ends up changing the color of the solution. Now, the question at the top of this is, does the coordination number of iron change? And does the oxidation number change? Okay? And let's go to the next slide. I skipped over this slide. We'll quickly do this for you because it's all the same. They end up being all the same. So the charge on each one of these compounds, and you can verify each one, is +3. Each one of these things is going to have 6 things bonded to the central metal, 6 atoms bonded to the central metal, so a coordination number of 6, which gives an octahedral geometry. So, same for all. That's not always going to be the case. We will see some other situations. 2 more slides, and we're going to work that out, okay? So this is slide 15. So we had our hexa-aqua iron in solution. Oh my goodness. Here's our complex. Here's our coordination sphere. Notice what's in brackets. When we put this in solution, these chlorides dissociate. Okay, and so we're going to be left with the hexa-aqua iron. And then here's the red solution, which was the other one with the thiocyanate ion, which I'm not repeating the name of. And then it has 2 chloride ions associated with it. Again, when we put this in solution, these completely dissociate. Okay. So let's take a minute. We're going to try to figure out the charge on the compound, the whole thing, not just on the iron. Okay. So what charge would be on the thing in the brackets? Okay. Figure out the coordination number, and then we're going to work on the geometry. Take a couple minutes, give it some thought, and then we'll work together. All right. Okay, so let's look at the charge first on these compounds. So again, when we put this hexaaqua iron complex into solution, it's going to form this. Okay, which means, and so basically all I'm doing here is taking those chlorides that are outside of the bracket, separating them from the complex, noting the charge. All right, total of -3 here. That means this has to be +3. Okay, and so charge on this compound, +3. What about for the bottom one? +2, yep. Okay, coordination numbers for the top, hexaaqua. 6. And what about for the bottom one? Not quite. Yeah, it's also 6. So there's 5 water for the bottom one, and then the thiocyanate ion as well. So total of 6. And because they both have coordination numbers of 6, that one's easy. You know they're going to be octahedral compounds. Questions on that? Yes? Coordination number in the first one is 6 because there are 6 water molecules bonded to it. Yep. Yep, in the bottom one, 5 water molecules plus 1 thiocyanate. Yeah, it's just number of things bonded to that metal atom inside the brackets. Yeah?
Can the coordination number ever be greater than 6?
We won't see a coordination number greater than 6. They do exist, but we won't see one. Yeah?
How do you know that the geometry is octahedral?
We know that the geometry is octahedral because there are 6 things bonded to the central metal. And we only have one option for geometry in that case. Yeah. If it was 4 things, now it could be either trigonal, planar, or tetrahedral. If it was 5, we also have one option. So. Other questions? Yeah?
How do you know it's octahedral again?
Because there's 6 things bonded to the central metal atom. And if we're looking at our geometry table, we only have one option for geometry when there are 6 things. Yep, so that one's nice and easy. Right, we won't see any lone pairs. Yeah, that's true, 6 bonded pairs. Right, so yeah, okay, let's go back to our geometry table. Okay, oh, here's our geometry table. Okay. Couple more things here. Mentioned some ligands and coordination chemistry. I have another table thrown in here in your notes. 2 things to see here. So we've been talking about thiocyanate. Thiocyanate and nitrite ion, these are interesting ligands because they can bond in 2 different ways to a central metal atom. See the or here with the arrows? So the thiocyanate can bond to a central metal through either the sulfur or the nitrogen, and this gives rise to isomers, and we'll talk about that. The nitrite can do the same thing. It can either bond through the oxygen or the nitrogen. Okay, they both have lone pairs that they can donate for the bond. So these are our monodentate ligands. All right. Monodentate meaning it can bind with from one spot on this ligand. We also have bidentate and polydentate ligands. Bidentate, meaning it can bind from 2 ends of one molecule. So a common example of this is ethylene diamine. Notice the abbreviation here. It's in parentheses real small, EN. You'll see this molecule show up in your homework. So be familiar with this abbreviation. It stands for ethylene diamine. And you'll notice that these two nitrogens are highlighted in yellow. Both of those nitrogens will bond to a central metal atom at the same time. And so what you would have is here's our central metal atom. We're going to have a bond to a nitrogen, a bond to another nitrogen. And it would basically make a circle kind of a thing, imaginative circle. Okay. There are many other ligands by pyridine. You might see that one show up. The others are, you might see oxalate, carbonate will show up. So make sure you're familiar with these types of things. Ethylene diamine, tetraacetic acid is kind of a cool compound. It binds in 6 locations to a central metal atom, and that's shown here. It's really useful. It's too far down the row. We use that ethylene EDTA in terms of chelation therapy. If you ever know someone who has high blood lead levels, they use chelation therapy to remove the lead from the blood and replace it with calcium. In terms of, here's another figure to show you ethylene diamine. We're going to have a demo on Friday where we try binding different amounts, stoichiometric equivalents of ethylene diamine to a central metal atom and looking at the changes that that gives. It's kind of a fun demo. But yeah, so you can see just sort of an example of what this structure would look like. And one last thing on these chelating ligands, or ligands that have bidentate or polydentate, that are bidentate or polydentate, they tend to be, or to form more stable complexes than compared to those that have monodentate, that are monodentate. So if you take a look at these equilibria, okay, back to chapter 14, 13, whatever it was, 15. Here we have a nickel complex. We put it in water with ammonia, and it forms this nickel ammonium complex with a formation constant of 1.2 times 10 to the 9th. If we do the same thing, but instead of using ammonia, use ethylene diamine, we form a complex with a much greater equilibrium constant. We get 6.8 times 10 to the 17. That one, as given, evidenced by the magnitude of K, that is a much more stable compound. Okay? So keep that in mind. I will see you all on Friday.